So, hello. I bought a lot of cool stuff for having good audio while recording videos, but it's all crap. So I'm using the built-in microphone here of my Huawei P40 Pro, which appears to be not too bad. So the noise cancellation is actually working quite good. Today I wanted to start a little series about hyperparameter optimization and neural network architecture search, and today I will start with random search or Montecarlo search and grid search just for the baseline. So let's start with the definition of hyperparameters, and we will contrast the parameters and hyperparameters. That's always a good thing to do first. If this is boring to you, you obviously can skip to the next video, which I'll upload soon. So a parameter in a neural network, also known as weights, they are actually part of fitting the network to your training data. So there's an algorithm called gradient descent, and this is responsible for finding a good set of parameters or weights to make the neural network fit your data. And obviously you have all these things like overfitting. That means you have a training set, validation set, and all that stuff. Okay, that should be pretty clear. Then the hyperparameters are something which are not part of the actual neural network. It's more about how the neural network looks like. So for example, the number of neurons and the number of layers and so on. And we can already see here that those parameters are influencing the architecture of the neural network. So if you tune a neural network with hyperparameters and those are influencing, for example, the number of neurons or the number of layers and so on, that's already considered as neural network architecture search. There are other hyperparameters, for example, the learning rate, the type of activation function in the neural network, the dropout layers, dropout rate, all those things are considered as hyperparameters. And now you have your training data, and your gradient descent algorithm will update the weights or parameters accordingly that you are satisfying your optimization objective. The thing is, if you change your hyperparameters, the performance of the whole algorithm, the whole neural network can be improved. But you cannot use gradient descent for finding those. The reason behind this is that the whole equation then isn't differentiable. That's another story, but what you need to do is you need to try out and find best hyperparameters for your actual problem. So the problem is the neural network and the data and your optimization objective, and depending on your hyperparameters, your optimization objective might become better. No? So that's why you need to fiddle around with the hyperparameters. And what I did and what we did as a community for a long time, we used our experience and a lot of patience, and we changed. We changed the number of layers, the type of layers, dropouts, and so on and so on. And then one side note, it's not only about the hyperparameters in the neural network. You can also introduce hyperparameters in your whole data processing pipeline. So everything what happens before the actual neural network training, so the data transformation, sometimes you create new features, sometimes you filter, sometimes you transform, sometimes you one-hot encode categorical columns, and so on and so on. And in those, often also parameters can be set. And you can also just include those into your hyperparameter search as well. Yeah, so, and now you have a set of hyperparameters, and let's say you have 20 parameters you tune, like learning rate, number of layers, number of neurons, and something in your data pre-processing pipeline, maybe not. And what you then basically get is a 20-dimensional space, vector space. It's easy, no? If you have two parameters, you can like draw it on X and Y. And in that plane you find different points, and each point is basically a selection of two parameters. If you add now a third parameter, you can imagine it as a 3D cube, and in that 3D cube, every point in that 3D cube is basically also a selection of 3 of those hyperparameters. And if you now go, for example, to my example, in 20 hyperparameters, you have a 20-dimensional vector space which you cannot imagine and which you cannot draw, but actually it's nothing else. You just search through points in that 20-dimensional space, and each point is a selection of a hyperparameter set. Yeah. So there are 2 brute force ways of doing it, and that's what I'm talking about today in this video. And later on I will come up with a more sophisticated one. So the most obvious one is called grid search. So you can basically say you have a 20-dimensional cube. This is your representation of all the possible hyperparameters, and you can mix and match continuous and discrete. So for example, number of layers is a discrete hyperparameter because it's only 1, 2, 3. And for example, learning rate is a continuous hyperparameter. It can be 0.9, 0.1, 0.01 and so on. And in those value ranges you can basically select anything. So in the continuous one obviously anything, and in the discrete one only the steps. But still you are searching in the volume of your hyperparameter space. And the most easy one, obvious one, is grid search. So what you then do is you define a grid. Obviously, if it's a discrete dimension, then it gets quantized to the discrete values. In the case of continuous dimensions, you need to do the quantization, and then you can just evaluate each point in that grid. And evaluate means you select a point in that hyperparameter space grid, and those hyperparameters you feed into your learning pipeline that includes the data preprocessing pipeline and the actual neural network, and then you train and then you evaluate the performance. And a variant of that is called random or Montecarlo hyperparameter search, and that's basically doing the same but not following the grid structure, but just randomly find points in that hyperparameter space and then re-evaluate the algorithm after each selection. Obviously, those 2 can easily be parallelized because they are completely independent, of each other. So if you have like 20 dimensions and you get, I don't know, 10,000 points in that hyperparameter grid or random grid, you can just evaluate them 10,000 in parallel if you have that amount of machines. Yeah. What else? One last thing. You obviously have heard about training set and validation set and test set. So if you do hyperparameter optimization, then you have to have 3 sets of your data. Obviously the training set remains the same, but the validation set then has to be somehow split, because if you remember, we do this magic with training and validation for the reason to prevent overfitting, so that you have a good performance on the training data only, and then if you see new data, the algorithm doesn't perform anymore. That's why you keep some data separate, that's the validation set, and then reassess the trained neural network with the validation data and see if it still performs equally. So now, if you tune your hyperparameters in the way I've described, then you're actually also prone to overfitting your hyperparameter against your training data, and that's why you need to keep a separate set which isn't involved in training or validation. That's the test set, and that you can use after you have finished your hyperparameter optimization. You can still use some unseen data to assess the overall performance of the neural network. Okay, that's all for now, and as promised, I will continue with some more sophisticated hyperparameter algorithms which are involved in hyperparameter optimization and also neural network architecture search. Those 2 fields are closely related. Okay, have fun, stay healthy and motivated. Bye.